University of Michigan in KIR when I have seen for the first time the ammonia vehicle, and also one other famous example from Toyota. And from these years, nothing really happened. Only there are some tentatives, for example, for hydrofuel ammonia incorporation. Okay, but perhaps some of you know that last year there was a big announcement between Toyota and also TAC that they will develop the first ammonia car engine. We don't know for the moment when it will be on the street, but until now, we never seen vehicle fueled with ammonia. I've seen also during the industrial academic workshop that there is a beautiful example for this joint research in order to develop 49 tons of traction trucks with ammonia engine. So it's still, we have still the idea perhaps to run vehicles with ammonia only. Okay, most of you know that from the announcement on the IMO roadmap in order to decarbonize the maritime sector, there is a lot of, in fact, impressive work about ammonia marine engine. And in 2021, there is an example of what we can imagine for the future on the sea. The ships will be fueled with a different type of fuel like ethanol, LPG, methanol, hydrogen, LNG, biofuel, and ammonia. Okay, so now there is plenty of industrial projects in order to develop, in fact, marine ammonia. So Wärtsilä, WinGD, MAN, EHE recently, and also Monday, I listened this new project with a CSSC manufacturer. So perhaps also we will see soon some ships with a marine engine fueled with ammonia. There are some other applications like tractor. There are not so many. I know only two on one project between Norway and Poland. But also there are interesting new announcements about, for example, to power train with also ammonia engines. So there is two examples. And why? Because it is not possible to totally electrify train everywhere on our planet. So there is other possible application where there is engine like genset, auxiliary power unit, off-road vehicles like construction, mining, port, cranes, and so on. And I am confident that it could be a very nice application and very good optimized application for ammonia engine. We can dream, so why not for aircraft? And here there are also some projects, not a lot. So there are some projects recently for a small company in Australia to develop ammonia Falcon business engine. But also there is a big project with Boeing. It started on University of Florida on SWRE on the NASA about how we can use ammonia in engine. Most of the time, in fact, they use ammonia as energy carrier and they will crack on board. Okay. Most of you, even if you are not in the combustion committee, you know that ammonia is not a good fuel. And it's not a good fuel for internal combustion engine. It is R2-inert. The flammability limits are very narrow. It has a slow flame propagation. And also, it's a fuel-bound nitrogen, so we will have some trouble with pollutant emission. So why we want to use ammonia in engine? The question remains, it is possible or not possible? In fact, we are going to the past. So during the 60s, there was several studies financed by US Army in order to see the potential of ammonia as fuel. First, they consider spark ignition engines and with a classical low compression ratio. And when they compare what's happened if we use isooctane or ammonia, sure, what they conclude, we will have higher fuel consumption. This is due to the low heating energy that can produce ammonia in comparison to classical engine fuel. But there are some things that could be good, like, for example, we can use ammonia in lower equivalence ratio than we can use with isooctane. So it's not always some drawback. If we look now on the energy output, the output that we can have from the engines, unfortunately, it was lower from the study, lower output of work, or higher sugar fuel consumption, and also it needs advanced spark timing due to the low velocity. Okay, what's about compression in an engine? Oh no, not yet, sorry. So in fact, from this study, they conclude that we need to increase the spark energy, we need to increase compression ratio, engine supercharging, hydrogen addition. So it was a long time ago already. And so finally, they said that, sure, we need to increase the compression ratio because we increase the combustion efficiency and we can extend the use of ammonia at high engine speed. So there is more recently a patent where they conclude exactly the same thing. We need hydrogen to assist ammonia. Okay, about compression ignition engine was worst because they conclude that in fact we need a compression ratio of 35 in order to obtain auto ignition of ammonia. So it's clear if we want to retrofit diesel engine with ammonia, there is no so many solutions, but we need to do something. So we can use the ignition by a small quantity of diesel tap fuel or add a spark plug in the diesel engine. There is no way. Okay, so now if we look what's happened between the 60s until 2015, no so many research, some vehicle, and what we can conclude, in fact, it was always dual fuel engine. So more of the time, 50-50%, no more quantity of ammonia mixed with gasoline, natural gas, alcohol, hydrogen sometimes, but not a lot, diesel, biodiesel, DME, what we want. Okay, but we know that now we have a good problem on the good problem, a new problem. What we want to reduce as well as possible our carbon footprint. So the question remains, how can we reach zero carbon footprint with ammonia engine if we continue to use, in fact, hydrocarbon fuels? But unfortunately, we know that we need something, ignition combustion improver. So I will consider mainly ammonia engine when we can use and guarantee the operating conditions with at least 95% of ammonia. For that, we have we can use a classical spark ignition engine, but with high compression, hydrogen, and so on. Or we can use a diesel type engine, but we need a small pilot of diesel type fuel or hydrogen or spark plug additions. So before I try to see what's happened on the review about the engouement of engine research. So we can see 2019 work, and we start to publish. So more or less we are alone until 22, and now you can see the number of papers that we can find only with ammonia engine. So it is exactly what say yesterday one of speaker for plenary session. It's impossible to read all paper. So sorry for some of you if I forget your work. It's not volunteer. So first we start with a current engine, okay, with our partner Peugeot. And we use a current spark ignition engine, but it was a single cylinder engine, gasoline direct injection, but used the fully premixed ammonia air. It was a very classical compression ratio, 10.5, so not very high. And this is what's happened when we start to do it. So it's an example at 1,500 RPM. The triangle represents, in fact, when we run with methane, the cycle with ammonia alone, on the stars, ammonia plus 15% of hydrogen. It was a very good surprise because we did nothing, and in fact, it works. Okay, we only change a little bit the equivalence ratio to see it to be at stoichiometric air-fuel ratio as we do, in fact, usually for gasoline engine. It's not so bad. We can have similar output energy and we can ignite easily. But sure, I can answer first that it is not really an utopia to run with pure ammonia. Okay, but in fact, when I want to change the load and when to change the engine speed, it was not the same history. So we can see that in red, I cannot ignite, and I need to add hydrogen. There is no other way to do it. But there are some new studies recently. When they use a higher compression ratio, it's 15, and they try to see it's possible to improve, in fact, ammonia ignition only by using very high efficient ignition system device. So for that, in fact, they use high current energy, for example, spark plug or high energy, or a spark plug with a multiple spark. And we can see that, sure, with high energy spark plug, we increase strongly the efficiency of the engine, and we can run with large conditions. They also change the ignition system by changing the ignition, the transistor coil, and they also obtain an increase, in fact, of the efficiency. So perhaps it's sufficient, and also they can run at a lower equivalence ratio, so it means to run with not full load, but lower load. Okay. As we decided first to try to see what's happened in different compression ratio, but unfortunately we had only diesel engine. So the easy way is to use a diesel engine and to add a spark plug. Most of people here who does some research on engine say that I am totally crazy, because in fact we can see in the difference between both engine. In spark ignition engine, I have a flow feed like that to create a lot of turbulence to enhance the flame on the combustion development. In the diesel engine, I have a flow like that, nothing about turbulence, and normally cannot work with a fuel like ammonia. Okay. When I try to compare what's happened with a spark ignition engine So this is with a spark ignition engine. We change a little bit the current ratio, but it is not something important here. What it is important, it is when I increase hydrogen content, I can run easily with a lot of stability at low load, which is very nice. It is my objective for the moment. But when, in fact, I use my diesel engine with my spark plug and I change the compression ratio, I can reach really lower load. So, in fact, it is a success. And this is totally strange because the turbulence inside my combustion chamber is really not for fuel air premixed. So what I want to say when I do that, be careful when we use only simulation, CFD modeling, and you said, okay, I have one engine like that, I replace gasoline by ammonia. It's not the truth, because until now, turbulent flame interaction in the case of ammonia is not well understood and cannot be well modeled. But it is not the truth. Okay, so what we conclude, in fact, yes, we don't need hydrogen. We need high compression ratio because can reach very lower limit without any problem. And this lower limit was similar to one study of Toyota when we enrich their engine with hydrogen. Another way also is to improve the ignition system itself again. So we did also by only use high power igniter. And this high power igniter in yellow, in fact, the conclusion it is that I don't need so high compression ratio. I can limit a little bit it. Okay, there is another way, the pre-chamber ignition. So the pre-chamber ignition is also a good example of how we can improve the ignition of the engine because it provides higher ignition energy and increase locally the turbulence. And we can have less global hydrogen consumption if we fill the igniter with hydrogen. But don't forget, my idea is to have only one fuel, which is ammonia. So how can we use pre-chamber igniter with ammonia only? Which remains one open question. Okay, so certainly I convince you that higher compression ratio, perhaps with some addition of hydrogens, if we want to cover the full operating conditions, optimize ignition, it's the ideal solution. Okay, but it is not so simple. In fact, some other problem remains, like how we will inject ammonia. Gaseous, liquid ammonia injection. Gaseous could be nice, but for that we need also a vaporizer. Okay, so we had also another material, which is always not so easy to control. We can have port fuel injection, but we will have a high intake cooling due to the vaporization heat for ammonia, or we can use direct injection. So this increases the volumetric efficiency, no air displacement or intake mixture cooling. Sure, it looks like nice, but if I compare, in fact, ammonia spray to gasoline one, by using the same injector, which was not developed for ammonia, it is the truth, it goes for gasoline, there is different spray shape, there is different atomization, in fact, behavior, and also very high local cooling of the ambient gases, minus 50 degrees Celsius, in the combustion chamber due to the vaporization of ammonia. This could be nice if we consider NOx emission, but it will depend when it will be during the cycle. Monday, I've seen that also this company developed its own injector, which is very important. On this, I'm sure that we have to do it. And the question remains, okay, to do liquid ammonia injection for engines is feasible, but we have to optimize again all the injection strategy as we did in the past with classical hydrocarbon fuel. We need to improve the injector. We need to improve the injection pump with the material compatibility and the safety. Okay, what about the hydrogen addition? Hydrogen addition sure is good because hydrogen is a zero carbon fuel, but it is not very nice for safety and for all global overview of the engine itself. We need another tank. So the idea is to use onboard reformer and to use partially cracked ammonia mixture. Just before me, the professor showed that they succeed on it to use it at a very low temperature. It was only 450 degrees Celsius, if I remember. And this is very nice. But when we calculate the input energy, when we add, in fact, the mixture of partially cracked ammonia as function of the quantity of cracking ratio, so this is a full 100% of ammonia, and here we cracked a little bit. In fact, we decrease the input energy in white. The consequence is sure we will also decrease the energy output. So we need more fuel. Moreover, I present Tuesday some recent work from Fabian Maus, and from the stick reactor model, they show that if we want to accomplish the driving cycle European standard one that we have for personal car, in fact, it means that we need to have at the reformer an ammonia flow rate between I cannot see 2000. Okay, between this quantity, which is really important, but it is not only this. But it is important. In fact, we have to provide a flexible cracker when we can change the ammonia quantity at the input to guarantee, in fact, the operating conditions of the engines and to avoid also some bad emissions. Here from the study, in fact, they show that it needs 600 degrees Celsius for cracking, but fortunately, it will be not the case. Okay, but it is not only a question of performance. It is also a question of pollutant emissions. So ammonia, it's a zero carbon fuel, so we can imagine that everything is perfect. If we compare with a fossil fuel, we know that there is several pollutants that we don't like, and also we can see their impact on the global warming. It's easy, CO2 plus N2O, black carbon, SO2, VOC, NOx, on NH3, on PM pollutant, and also we can have also some trouble with the ozone layer. What about ammonia engine? Unfortunately, there is what we can call ammonia combustion emission risk triangle. And this, we have to compete between these three problems: unburned ammonia, which is very high toxic molecules, NOx, which is not good for the health, and N2O, as it has about 300 times the global warming importance. So, in fact, the question remains, what's happened with NH3 from this effect on our planet? Okay, if we look on the previous study, in fact, in this study, as function of the output on the power of the engine, they plot, in fact, the NOx emissions. In comparison, there is what we can have from gasoline. On one, we can have with gasoline plus NH3. It was not pure ammonia. Okay, and what we know from gasoline, it was only thermal NOx, and for ammonia, it's thermal NOx plus fuel NOx. If we look on some old kinetics mechanism where it takes account of the fuel NOx, we can see that in fact the fuel NOx can be produced at lower temperature than thermal NOx. So we don't know what will happen with ammonia. Recently, there is the beginning of the T map that it was done previously for hydrocarbon fuels in order to predict soot and NOx. And here it's for NOx on N2O. So what we can see, it's NOx is produced mostly after a temperature higher than 1500 Kelvin in lean mixture. But for the case of N2O, we can see that we can produce it at any equivalence ratio and mainly at lower temperature. So there is another question, what about ammonia? Ammonia, it will be produced perhaps only in the rich mixture, perhaps, but you can have also unburned ammonia due to the fact that you have some crevice in the engine. So what could be the effect of hydrogen addition in order to mitigate in fact, this pollutant? The recent study show that in fact, when we go from the lean mixture to the rich mixture, sure, as expected, I have more unburned ammonia in rich mixture, but I can have also unburned ammonia first in lean mixture due to the instability of the engine. And also here, I have one quantity of ammonia which is not zero, and this is mainly due to the crevice problem that we can burn ammonia later during the cycle. About NOx, it's quite similar to what we can imagine. We produce mainly NOx in lean mixture. About N2O, there are some good news. In fact, N2O remains very low. Most of the case, it's lower than 100 ppm. Okay, so we try to see also what's happened when we use partially cracked ammonia. So by adding H2 on N2, and what we can see, so here we have ammonia at the exhaust, NOx, and what we can see, for example, here, 100% ammonia, and we increase the quantity of cracking ammonia, we decrease the ammonia at the exhaust, but we increase NOx. Even if we have less, in fact, fuel NOx, we increase it due to the presence of more hydrogen. The decrease of ammonia is due to the fact that we burn better the ammonia content, even if I consider, in fact, to consider the real ratio between ammonia at the exhaust in comparison to ammonia that I put at the intake. What's about some other pollutant that we never talk about? Because many companies told me, but Christine, there is no regulation about hydrogen at the exhaust. And it's true, there is no regulation. But in fact, when you use ammonia in engine, as function of the operating conditions, we can have at the exhaust some hydrogen. So it's not a small quantity because it could be, as you can see, it could be until, for example, 2% at the exhaust. 2% is could be the same level of ammonia that we can have at the exhaust. It's not the same problem. Hydrogen is not toxic. But for safety reason, it's not also good to have it. Okay, about N2O, we find similar things, but it remains below 100 ppm. Okay, so H2 also increase when we have in situ cracking of ammonia. So as a summary, in fact, we can compare emission from ammonia engine that what we can get from classical hydrocarbon gasoline engine. So in black is for natural gas, in red for ammonia. The main difference is sure we have no CO, okay, but we have hydrogen, and unburned hydrocarbons are unburned ammonia. So it's really similar. So there is no way we need to mitigate to find a strategy in order to avoid that. Okay, the easiest way is to think about after exhaust post-treatment. And most of people think that selective catalytic reactor is the solution, and it is already done because it exists for diesel engine. True. It's one way to remove, in fact, NOx. But it is not mature for ammonia engine. First, the first idea was to say, as we produce ammonia in the exhaust, unburned ammonia on NOx, we don't need, in fact, to add ammonia in the exhaust like we add urea. It could be true if we can control, in fact, the NOx NH3 ratio as function of the operating conditions. Moreover, don't forget, ammonia engine will produce no CO2, but in the other end, it produces a lot of water in the exhaust. It's good to have water, sure, but it will be between 25% until 30% of water in the exhaust. So it means that until now, we don't know the life duration possible for this kind of SCR. So the catalyst has to be changed and to be improved also. Okay. Also, my colleague from the University of Nottingham, they try to see how it's possible to optimize the ratio ammonia-NOx in order to guarantee the well working of, in fact, the SCR. For that, they adjust the hydrogen content in the ammonia and to see how it's possible to regulate unburned ammonia and NOx at the exhaust as function of the quantity of hydrogen that we have to add at the intake. And this could be a real nice control of the emissions at the exhaust. So hydrogen could be also one way to optimize SCR efficiency. Okay, before I will conclude, I cannot forget ammonia compression ignition engine without a spark plug. So I decided to show with you a recent study done in US. Why? Because in fact, to use a pilot fuel is not good because we will have some CO2, but in the other end, it could be very useful because in many ships, it's usual to have several tanks and different fuel in ships. And also, we don't know in the future where we can have easily ammonia in different airborne. So perhaps they have to change the fuel as function of their trip. So to have two tanks is not a problem for ships. So we have different strategies, sure, to ignite ammonia with a small quantity of diesel. It will be a function of the diesel injection itself during the cycle. For that, they consider that ammonia air charge is already fully premixed, so they adjust only the injection of diesel. And I present something when in fact they inject very late, like in a classical diesel engine. And if we look on the operating condition map, so the energy output on function of the engine speed, we can see that they can replace at least 95% of the fuel by ammonia, especially at full load. But unfortunately, it remains difficult at low load, and they cannot reach a very high replacement, but they guarantee at least 50% of ammonia replacement also at low load. Why I want to show you that it's about the emissions. So if we look on the emissions when we are at full load with more than 95% of ammonia, sure, for the two cases, NO is very high in comparison to classical diesel combustion mode. And unburned ammonia is also one problem. But if we look on N2O, we can see that N2O finally is not so high when we are in fully charged, fully load. And but don't forget that N2O has 300 more or less GWP CO2 equivalent. So it means when we want to compare classical fuel with ammonia engine, if we transform N2O emission in equivalent CO2, this is what's happened. Finally, they cannot reach more than 80% of reduction of CO2, even if the quantity of ammonia is more than 95%. So my conclusion, can we run ammonia with only ammonia? I will say yes. Can we have a very clean 100% ammonia engine? Yes, but it is not so easy. We need also to resolve a lot of challenge. It can be technical, but also it remains a lot of challenge scientifically. So I like also to let this table. It was done by my first PhD student on ammonia engine, but it remains the truth. So we need more fundamental experiments, not only in engine, but before engine, to really well understand ammonia combustion. And after, I have no time, but there is so over scientific challenge about lubricity, materials compatibility, and safety. Last, I don't forget that most of these experiments have been done for light duty, small heavy duty engines, but most of the time never with large engine that we can have in the ships. So many people can say, we don't need your work. It's not true, because if we want to develop very accurate model, we need to have experimental data for at least a small scale before to apply it for all larger scale engine. Thank you.
let's go and enjoy the cruise. See you in a